All right, so let's do an example of figuring out if a series is absolutely convergent, conditionally convergent, or divergent. The series we're going to consider is the following. The series from n equals 1 to infinity of cosine of n all over n squared. Now, what's tricky about this series this is not alternating. Okay. Remember, as n goes from 1 to infinity, cosine is going to keep bobbling up and down forever. And at some point, there's going to be terms. At some point, there's going to be a couple terms that are positive in a row, a couple terms that are negative in a row, and so on. So this is not alternating. So let's try to figure out if this series is absolutely convergent. For these types of problems, that is the first thing to do. So for absolute convergence, we throw absolute values on. So the series we consider now, from n equals 1 to infinity, the absolute values around cosine of n all over n squared. And well, we could rewrite this a little bit at this point. We could write this as the series, from n equals 1 to infinity of the absolute values just around the cosine of n divided by that n squared. And the reason is we know n squared is always going to be positive. And that cosine of n, like we saw before, well, that is a thing that's going to bobble between positive and negative, but there might be a few positive terms in a row followed by a few negative terms and so on. It's not going to be purely alternating. So let's stare at this series and ask what we can do to decipher, does this converge? And at this point, this series only has strictly positive terms because the absolute value is keeping that numerator always positive, the n squared is always positive. So we're thinking we could do something like an integral test, or we could do a comparison test. Those seem to be our options here. And well, I don't really want to integrate a cosine in absolute values just because it seems like it might be a bit tricky. So I'm going to first attempt to do a comparison test. So again, we're still testing whether or not this series is absolutely convergent. At this point, we just have a series in absolute values that we're testing for convergence. So for comparison tests, we need to figure out a series in which to compare to. And the way that we did that before was ask ourselves, well, for large n, what is the main contributor in the numerator and main contributor in the denominator? So in this case, well, we only have one thing in the numerator and we only have one thing in the denominator. So for large n, this still looks like the main contributor in the denominator is an n squared, and the numerator, it's still that absolute value of cosine of n. But this is where we can use a little more mathematical reasoning and flex our math muscles a little bit. Since we know that cosine at most could be equal to 1, or at least at minimum could equal -1. We know in absolute values that cosine of n is always going to be less than or equal to 1. So we could try comparing now to this series, because we know that series on the left, if that cosine is less than 1, well, it's going to be smaller than that series on the right. So, what does the series on the right do? Well, again, this is one of our friends, the p-series. In this case, p is equal to 2, it's greater than 1, so this converges. Now again though, we haven't shown that our series with that absolute value of cosine over n squared converges. All we've shown is the series we're comparing to, that converges so far. So 3. How can we set up this inequality? Well, remember, we have cosine of n all over n squared, and that cosine of n is in absolute values, and we're comparing to just the series of 1 over n squared. And well, we kind of did this already, right? If we're showing that our series, or the series that we compared to, converges, we want to show that our series is smaller than a known convergent series. Again, the reason for this is, well, if we can actually show that our series is less than or equal to a known convergent series, while also saying that our series is greater than or equal to 0, it forces our series to be wedged between 0 and that value of that known convergent series, so it must also converge. And well, the way that we set this up, we could try to, and we know that our series is always going to be greater than or equal to 0, just because we have purely positive terms that we're adding together. And in this case, we could cross multiply, so we get n squared times the absolute value of cosine of n, in absolute values, of course, and we were trying to show that it is less than or equal to n squared on the right. Remember, all we did was cross multiply here. And well, since n is going from 1, 2, and so on, n does not equal 0, so we could divide n squared from both sides, and we have the following inequality, that cosine of n in absolute values is indeed less than or equal to 1, because cosine at most can take on a value of 1. So this is true. So therefore, we've set up our inequality correctly. So to synthesize all of the information here, since our series in absolute values is less than a known convergent series, it must also converge. But remember, that's not all. Since we threw on those absolute values, since we tested a series with absolute values and we saw it converges, that series is absolutely convergent. So our original series is absolutely convergent. So again, to walk us through this problem, we started off with this series from n equals 1 to infinity of cosine of n over n squared. This is not an alternating series. There would be a couple terms at some point that are both positive in a row, followed by a couple terms with negative in a row, and so on. To test whether it's absolutely convergent, we threw absolute values on each term and then tested the series from n equals 1 to infinity of the absolute value of cosine of n over n squared. And we saw that this converged. And because that series with absolute values converged, we're able to say it is absolutely convergent. It just so happens that we showed the series with absolute values converged using a comparison test. So there's a couple steps and levels of this problem. Next, we're going to introduce a series convergence-divergence test for absolute convergence called the ratio test. Stay tuned.